Good afternoon, everyone. My name is Xiaoyan. I come from Intel Open Source Technology Center. Okay. Today I will introduce some my experience about BlueStore performance tooling. Yes, that's all. And okay, so at first, let's look at the overview of Ceph. And the Ceph includes Ceph management service, Ceph monitor service, and OSD service. And OSD service provides the data storage functions in local load. Inside OSD load, object store, object store provides the is used to save data. Okay, and currently BlueStore is the default object store. Yeah, and let's look at the overview of BlueStore. This picture is from Sage, I think. Okay, and next file store. File store uses file system to store its data. Okay, but for BlueStore, it operates the raw disk directly. So it includes two parts. One part is the custom data are written into the disk directly, and the other part is the BlueFS part. Above BlueFS, we will open RocksDB to save the metadata. Okay, there are several main kinds of metadata. One is the object mapping data. It is used to store the mapping relationship between object and the real address. And the second one is on-map data. It includes some attributes related to an object, okay, and plus PG logs. The third one is default logs. I will talk it later, okay? So, and the other metadatas. Okay, and the next is BlueStore. This is the mechanism of BlueStore. Okay, in the memory there are there is one active RocksDB memory table and several immutable memory table. Immutable means can't update. Okay, in the disk there are log file and other SSD files. Okay, when a write request comes from clients, it at first insert the data to the active memory table, and meanwhile write it into the log in the disk, and after that it can return to the client. The I/O is complete. Okay. Forgot to say, memory table is a memory space with a fixed size. Okay. In BlueStore, the default size for the memory table is 256 megabytes. Memory table includes skip list or other data structures. When we insert a key value to the memory table, it will do sort. Okay. Once the active memory table is full, it will change the active memory table into immutable memory table and create another active memory table for later write request. Okay. So we have a limitation. We have a limitation for the immutable memory table. So if the number of memory table exceeds some limit, we need to flash the immutable memory table into the disk. That is level 00 SSD file. Okay, and when the number of L0 SSD files exceed the number or the capacity of level 00 SSD file exceed some limit, it needs to compact the level 0 files into level 1 and so on. That means the data in the level 0 files are all latest. Yeah, RocksDB at first is development by Google, that is DB, and later improved by RocksDB, by Facebook, and renamed to RocksDB. Okay, this topic will focus on the random write process because their performance maybe needed to improve. Okay. As we know, BlueStore, the disk is allocated in minimum allocation unit. Okay, I think for SSD default size is 16 kilobyte. Yeah, and based on the data alignment and data size, we divided the write request into small write and big write. Big write is first drop write. Okay, let's look at the data flow of small write at first. When customer the write request comes to BlueStore, at first BlueStore do some handle which data need to go to the disk and what kinds of metadata need to update it. Okay. For a small I/O, RocksDB acts as a channel or like a cache for a small I/O. That means at first, the custom data won't be written into the disk. Instead of, they are submitted to the RocksDB with other metadata. Okay, so after the customer data and metadata are updated in the RocksDB, the write request can be returned to the app layer. The I/O is completed in the BlueStore. Okay. After that, in the background, BlueStore will write the custom data back to the disk, to the original space of the disk, and then it deletes the custom data in RocksDB. Okay, by the way, the custom data written into RocksDB is also called default logs. Okay, and then this is big write flow. Okay, same as small write. At first, it needs to handle the data. What kinds of data need to go to the disk, and what kind of metadata should be updated. Okay, here then BlueStore will allocate a new space for okay. Word writes are rewrite. Okay, a rewrite process. Okay. And then BlueStore will allocate a new space in the disk, and then write the custom data to the new space. And after that, the updated object mapping metadata and other metadata will be written to the RocksDB. Once the RocksDB completes the operation, the I/O is completed, we can return to the app layer. Okay, in the background, BlueStore needs to release the original data space. Yes. Why the I/O flow is so complex? Because we have to keep data integrity. No matter whenever the server fail, either we get the data before this write request, or we get data updated. Yes, that means there's no times we can get half of the old data and half of the updated data. Okay. This is my test. Okay. I did 4K random writes test. At 4, the pie chart, the total latency is OP underlying W underlying latency. That is latency in the OSD. And BlueStore latency is BlueStore commit latency. That means BlueStore receives the write request and then after that it gives back to the OSD. Okay, from the pie chart you can say BlueStore is the main part, but for the other part it was a lot small. Okay, so I had to check from for the port dump. Yeah, this data from the port dump. Okay. When I checked the port dump, I found that the BlueStore finisher took a lot of time. Okay, so from because I use SID to do test, the BlueStore by default the BlueStore finisher is single thread. From the port dump data, I found that the queue is longer, the queue is long, and the latency is high in the BlueStore finisher. So I enable, I make the BlueStore finisher multi-thread, and I did a test again, and then I get the bottom chart, the LPS increased. Okay, after I enable the BlueStore finisher multi-thread, the pie chart becomes like that. Okay, BlueStore is the main L latency in the OSD latency. The left column is 4K random write, and the right column is 16 random writes. The bottom chart is latency inside the BlueStore. You can say there are two kinds of L latency, main latency in BlueStore. One is KVQ. One is KVQ latency. That is when metadata are submitted to the RocksDB, they lead to queue. So the queue latency is high. So the wait latency is high. And then we submit the metadata to RocksDB. That is the committing latency. This time is RocksDB handle the metadata update. Okay, so both for 4K random write and 16 random write, that is small write and big write, the RocksDB, the latency of RocksDB is high. Okay, and then I did some tests to tune the RocksDB's parameters. Okay, we know that at first I keep the total of memory used by RocksDB constant. Okay, and then I change the size of meta tables and change the size of every memory tables and the size to flash one time. What does it mean? It means when we flash the memory table into the disk, every time we can flash one memory table or two memory table or three memory table and so on. Okay? Yeah. So this is the right chart is the LPS and the different red buffer number and red buffer size. Okay. You can see that why we decrease the memory table size? We know that every memory table is a skip list or tree or something like that. And if the size of memory table is small, that means every time we insert the data, the key value data into the table, the comparison number is nice. Okay. We can why we flash 2 memory tables or 3 memory tables at once? Because if we the more memory table we want to merge, the less data we write into the RocksDB. But also we need to notice that if we flash more memory table, we need to take more CPU time. Okay, from the chart you can see when the memory table is 128 or 64K megabyte, and the size of flashed memory table is about 512. The performance are best. Okay. Meanwhile, I was thinking whether I can increase the total memory used by RocksDB so that the I/O performance can be improved. But when I did such a test, I changed the total memory to double or triple. The I/O performance improves little. Okay, so then I got the research about what kinds of data would be written into RocksDB and RocksDB disk. The above chart describes the data written to RocksDB. That means BlueStore written to RocksDB. The horizontal axis is every memory table. Okay. In every memory table, default logs is most, and then object mapping data, and then PG logs, and then PG logs. Yeah. Other metadata are little. Okay, and let's look at the bottom chart. That is data written to RocksDB level 00 disk. Okay, for every level 00 SSD file, the most is object mapping data, and then PG logs. Okay. Oh, the former one is random 4K random write, and this chart is random write 16 random write. Okay. Per every memory table, object mapping data is the most, and then PG logs. And for every level 00 SSD file, object mapping data is the most, and then PG logs. Okay, so from the charts for 4K random write and 16 random write, both object mapping data and PG logs are the most data. Okay, I have ever did such test. Okay, because we want to decrease the write amplify of the RocksDB. That means we want to decrease the data written to the disk. Okay, at first, currently in RocksDB, they merge the memory tables and flash the data to the disk. That means, for example, here we merge memory table 1 and memory table 2, and then flash the data to the disk, so that where the data invalid in memory table 1 will be deleted, but the invalid data in memory table 2 won't be deleted. For example, I write A into memory table 1 and then delete in memory table 2. Okay? So when flashing, the data A will be invalid. Okay? But if I write the data A in memory table 1 and delete it in memory table 2, and then in memory table 2 I write the data A again and deleted it in memory table 3. But when RocksDB flash data memory table 1 and the memory table 2 into the disk, it still write the data A into the disk. Okay? So we had a solution to merge the data recursively. That means we compare data in memory table 1 with the later memory table, maybe 1 or 2 or 3. For example, if we compare memory table 1, the data in memory table 1 and memory table 2, and then we flash the valid data in memory table 1 into the disk. And then for the second run, we compare the data in memory 2 with the memory table 3, and then we write the left data, that is the valid data in memory table 2 to the disk. Okay, and that means the comparison is recursive. Okay, as a result, we got the chart over there. It can somehow be improvement, but not much. Yeah, this is the future work I would want to do, because for PG log, every time PG log is written to the RocksDB, we read it only when OSD node fails. We want to do recovery, we read the PG log. Okay, so currently, from my opinion, RocksDB is too heavy for the PG log. Maybe we can provide some journal for the PG log, something like that. Okay, and for the object data, maybe RocksDB can work. Okay. Yeah. Yeah, that's all. I think. Yeah. So, any questions?